Okay, time for another exciting lesson. This time we're going to talk about naming and formula writing. So I'm sure you guys remember this from last year. I'm going to fly through this, especially since we're going to cover this in even more detail through a reading that I give you, and we're going to practice this quite a bit in class. So I don't know that I need to go into a lot of detail here. In fact, I don't think I put blanks in these notes because there are quite a few sample problems. So we're just going to rush through the note part of it and hit the sample problems. Alright, so here we go. Diatomic molecules. Hopefully you guys remember those from last year. If you were in my class last year, I told you to remember the number 7. And the reason for that is because it starts with the exception of hydrogen, which is kind of over here by itself. There are 7 of the diatomic molecules I want you to remember. And nitrogen is number 7 on the periodic table. That's its atomic number. And it sort of makes a number 7 if you look at it. And so you go from nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are 6 of them. And then if you remember that there's 7 total, then hopefully you'll remember hydrogen is the weird one that's off by itself. Okay, so that's the diatomic molecules. Those are the ones that can never be alone by themselves in nature. They can, but they don't like to be at all. Naturally, they occur in pairs. Okay, types of formulas. We've got empirical formulas and we've got molecular formulas, okay? And I think you guys remember those from last year. Empirical formulas are the lowest whole number ratios. Molecular formulas that's exactly what's in the compound, okay? So an empirical formula might not be exactly what's there. It's reduced to the lowest ratio, okay? So an example of that, C6H12O6, that is a glucose molecule. Okay, that's a molecular formula right there. The empirical formula for that would be CH2O, because we reduced it down to its lowest amount. Okay, some other types of formulas you might see. A structural formula, like this one up here. Structural formula is going to show the order the atoms are bonded in. Okay, so it's going to give you a little bit of an idea about the arrangement. You can also have a perspective drawing, and we did these, I think I showed these to you last year. I don't know that I actually made you draw any. But these basically just show a little bit about the shape of the molecule, but it's kind of a rough sketch of the shape. Let me go back here. The other two models here, ball and stick and space filling, both of these also give an idea of the shape, but they're a little bit more artistic in the way they show the three-dimensionality, so it's a little bit easier to see sometimes exactly how the molecule or the compound is shaped. Okay, so those are the types of formulas. Okay, we got a sample problem here. Write the empirical formulas for the following molecules. Glucose. Okay, I'm going to, let's see, open up a notebook file here and we'll do all our practice problems on that. Where's my everything else? Oh, that's why. Okay. So we're going to open this up, and we want to, actually I already showed you the example here. Writing the empirical formula for glucose, C6H12O6, and we wrote that as CH2O. So I can probably skip over that one. We'll go straight to B. And letter B here, it says nitrous oxide, a substance used as an anesthetic and commonly called laughing gas. Molecular formula is N2O. Okay, so we want to write the empirical formula for N2O. This is letter B, I think. I'm going to put this down. Here we go. The empirical formula is N2O. The formula they give us is N2O. They want to know the empirical formula. It's the same. Okay? Empirical formula is N2O because 2 to 1 is the lowest possible ratio that you can have there. Alright? So that's pretty simple stuff. Back to this. Okay, so ions. When atoms lose or gain electrons, they become ions. You guys know that. If they lose electrons, then they're going to become positive. If they gain electrons, they're going to become negative, because remember, electrons are negatively charged. Cations are positive, and the way that you can remember that, you can't see me doing it. Cations are positive. Okay, cations are positive, so you can remember it that way. Anions are negative. Cations are found on the left side of the periodic table. All the metals are going to form cations. So they didn't include this in here, but all the transition metals will also form positively charged ions. The anions are negative. You're going to find those on the right side of the periodic table. Those are the ones that when they form together, they typically form covalent compounds. If you have a metal and a non-metal combining, then you're going to form an ionic compound. Okay? Alright. Next one here. And I think maybe I'm going to not go to full screen so much anymore, because I think that's slowing me down. Okay, so back to this. Give the chemical symbols including mass numbers for the following ions. The ion with 22 protons, 26 neutrons, and 19 electrons. Alright, so if we want to write this chemical symbol here, letter A, 22 protons. Okay, well, first thing we need to know is what symbol do we actually write, because they didn't tell us what atom it was. So if you look on the periodic table, we're looking for an atom with 22 protons. Okay? And that's going to be the one that has the atomic number 22, because remember, atomic number tells you the number of protons. The element on the periodic table with atomic number 22 is Ti. So we're going to write Ti here. Okay? It has 22 protons, so we're going to write a 22 down here because that's the atomic number. Always goes down there. There are 26 neutrons and 19 electrons. Okay? So if you add up the 22 protons and the 26 neutrons, that's the mass number. The number of electrons doesn't go on the left side. That's going to have something to do with what we write on the right side. Okay? So add up the 22 protons and the 26 neutrons. That gives you 48 for your mass number. And then the 19 electrons does tell us something. That tells us this is not a neutral atom. Okay? Because in a neutral atom, it would have 22 protons and 22 electrons. So what we have to do here is we realize it has 3 less electrons than it does protons. Protons are positive, electrons are negative. If it has 3 more protons, then it must be a 3+ ion. Okay? And so that's how we would write that chemical symbol. Okay? The next one, they're a little bit nicer. They tell us that it's sulfur, and they tell us it's an ion. Okay? So we got sulfur, but now we have to look up something different because they didn't tell us the number of protons. So you have to look up sulfur on the periodic table. It has atomic number 16, so that's the number that goes on the bottom. And it has 16 neutrons, so we're going to put a 32 up here because 16 protons plus 16 neutrons gives us 32 for the mass number. This also has 18 electrons. Now it has 2 more electrons than it has protons, so this is going to have a 2- charge. Okay? Alright. The next sample problem on here, predict the charges expected for the most stable ions of barium and oxygen. Okay, now we have to start thinking about the periodic table and where these things are located. Barium is in the second column on the periodic table, which means it has 2 valence electrons. Okay, hopefully you remember how to find the number of valence electrons that something has. If barium has 2 valence electrons, the easiest thing for it to do to form an ion is to lose 2 electrons. Okay? If it loses 2 electrons, it's going to become positively charged because the electrons are negative. Okay? So barium's going to be a 2+. Oxygen is in group 6A, or group 16 on the periodic table. That means it has 6 valence electrons. And remember, the goal here is to get to 8 valence electrons, to have 8 in your outer energy level. Okay? So oxygen, in order to get 8, needs to gain 2. If it's going to gain 2 electrons, then it'll have a 2- charge. Okay? Alright. Next sample problem, which of the following compounds would you expect to be ionic? N2O? Okay, so let's talk about N2O first. That's nitrogen and oxygen. They are both on the same side of the periodic table. Remember, ionic They're going to be on opposite sides. Okay? Covalent, same side, and maybe I should also write in parentheses here, opposite sides. This is going to be a metal and a non-metal. And then here, it's two non-metals on the same side. Two metals do not form a covalent compound. It has to be two non-metals. So two on the right side. Okay? N2O, since they're both on the right side, that's going to be covalent. Na2O, sodium's a metal, oxygen's a non-metal. So Na2O would be one that we would expect to be ionic. CaCl2, calcium is on the left side, it's a metal. Chlorine's on the right side, it's a non-metal. So CaCl2 would also go on our list here. SF4, sulfur and fluorine are both on the same side, and so that's going to be covalent as well. Okay? Alright, back to this, writing formulas. Okay, so when we write formulas, and hopefully you can see this, I'm trying not to enlarge it because that causes me some problems here. But when you write a formula, you're going to look at the charge on the ionic compounds, and you're going to do what we called crossing charges last year. Okay, you look at the charge that each one has, and it becomes the subscript on the opposite atom. Okay, and so there's a picture of this that's drawn in here for Mg2 plus. It's really hard to see on the sheet. Sorry, Mg2 plus and N3 minus. Okay, the 3 crosses down and goes here. Okay, and the 2 crosses down and comes here. Alright, so you end up with Mg3N2. So a sample problem on that one. The empirical formulas of the compounds formed by Al3 plus and Cl minus. Okay. So the empirical formula here, if we've got Al3 plus and we've got Cl minus, we're going to crisscross, and we end up with AlCl3. Okay. For B, it's Al3 plus and O2 minus, and if we crisscross those, then it's going to be Al2O3. And then if we have something like Mg2 plus, and now they're throwing a polyatomic ion at you here, NO3 minus, we're going to have to talk about those polyatomic ions again. We'll talk about that a little bit more tomorrow. So Mg2 plus, cross that over, it's a 1 minus here, cross that, you end up with Mg. Now this is tricky. You have to put the NO3 in parentheses. I'm sure you guys remember this from last year, and then the 2 goes outside the parentheses. MgNO3 2. Okay? That's how that works. This chart down here gives you some common cations that you can have. So you can take a look at that if you want to. And then the next chart also gives you some common anions that you might have. Now this also includes some polyatomic ions on it, okay? I'm going to give you a sheet on Monday, and that sheet is going to have a list of polyatomic ions on it. Now, I'm going to give you that probably for your first, maybe second quiz. By the time we get to the first test, you need to have that list memorized, okay? Because they do not give you those polyatomic ions on the AP exam. You need to know these, okay? And I'll tell you which ones that I think you should know. All right. Inorganic nomenclature, okay? And what that basically means is naming and writing formulas for inorganic compounds, okay? Inorganic is all we talked about last year. We're going to mention organic a little bit, but when I say inorganic nomenclature, all I mean is the naming and formula writing we did last year for both ionic and covalent compounds, okay? There's some new weird terms here. I'm going to enlarge this for a minute here. So, patterns in oxyanion nomenclature. Now, those of you who had Ernst, you may have talked about oxyanion. I don't think I mentioned that term in my class. But an oxyanion basically is just an anion that has oxygen in it. Kind of makes sense, right? Oxyanion. So we're talking, you know, SO4, 2 minus, ClO4 minus, that sort of thing. Okay, that's an oxyanion. In other words, most of the polyatomic ions. That's really what we're talking about here. Okay. So I said we're going to talk about that tomorrow. We're going to talk about it today too, and then we'll talk about it in a lot of detail and practice it in a lot of detail on Tuesday in class. Okay. When there are two oxyanions involving the same element, the one that has the fewer oxygens ends in ITE. Okay. So an example here would be NO2 minus is nitrite, SO3 2 minus is sulfite. Well, the problem there is you sort of have to know how many oxygens it normally has. Okay, so you have to know that NO3 minus is kind of the most common polyatomic ion there, and that would be the nitrate. That makes the NO2 minus the nitrite. And then you have to know that SO4 2 minus is the most common form of sulfur and oxygen combined. So that's going to be the sulfate. And then when you have one less oxygen than that, it's sulfite. Okay? The one with the more oxygens ends in ATE, and that's just when there are two oxyanions, okay? Two only. Now sometimes you can have more than two. So then again, NO3 minus is nitrate, SO4 2 minus is sulfate. I would memorize the 8s, and then you can figure out everything else from the 8s, okay? As long as you know the ones that end in ATE. All right. So here's another example, chlorite, ClO2 minus. So that would mean that ClO3 minus is chlorate. And this is going to be, okay, it's clearer in your notes than it is on here, but when there are more than two oxyanions, here's the scenario on this one, okay? So the one with the second fewest oxygens here, let's say that we have four different combinations. We have ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus. Okay? We have all of those. So the one that ends in the second fewest oxygens, or has the second fewest oxygens, is going to end in ITE. Okay? So ClO2 minus is chlorite. The one with the second most oxygens, right here, ends in 8, chlorate. Okay? And then the other two are a little bit more tricky. The one that has the least number of oxygens overall, you put a hypo in front of it and you leave that ITE ending on it. Okay? And then the one with the most oxygens, ClO4 minus, you put a per on the beginning of it. Okay? So it goes per 8, then 8, then ite, then hypo-ite. Okay? And so hopefully that makes sense there. You've got that diagram on your sheet. Okay. What do we have here? Oh, sorry. That's what we just covered. So we can skip through that real quick. Okay, let's talk about acids for a minute. No, actually, let's do some sample problems first, and then we'll go to acids. Okay, so sample problems here. The formula for the selenate ion is SeO4 2 minus, right? The formula for the selenite ion. Okay, so remember, selenite is going to have one less oxygen in it than selenate. Now, the kind of tricky thing about these is that they combine in such a way that they're going to end up having the same charge, okay? So the charge is going to be the same, it's just the number of oxygens that's different. So selenate is SeO4 2 minus, selenite would be SeO3 2 minus, okay? Next one, name the following compounds. K2SO4, draw a line here. K2SO4, that's potassium, and SO4, again, you just need to memorize that one. That's going to be sulfate. Okay, so the way we would name this here, this is potassium sulfate. Okay, next one. Barium hydroxide. Oops, I just said it. Ba is barium, OH minus is hydroxide. You guys might have remembered that from last year. So that's barium hydroxide. Okay. And then C here, FeCl3. Fe is iron, Cl is chlorine. Okay. So this is iron, just chloride, because this is not a polyatomic, so it doesn't end in ATE or ITE or anything like that. But there is a twist here. Iron is a transition metal. So I don't know if you guys remember this or not, but when you have a transition metal, you have to tell what the charge on the transition metal is. And the way we figure that out, chlorine is always a 1 charge when it's in an ionic compound, because it's in group 17 or group 7A. Okay, so chlorine's a 1 charge. That means that if it takes 3 of those chlorines to combine with the iron must be a 3 plus charge. And we have to put a Roman numeral 3 here to show that this is iron 3 plus combining with the chloride. Okay, so you just got to remember to do that with the transition metals, and it's easy to forget. All right, last sample problem here, and then we'll stop this video and pick it back up on the next one. Write the chemical formulas for the following compounds. Okay, so now we're going backwards. They're giving us the name. We have to write the formula. Potassium is K. Sulfide is just S, sulfur. Okay, now what I like to do on these is I like to go ahead and put the charge that they usually form based on where they are on the periodic table. Potassium's in group 1, so it's going to be a 1 plus charge. Sulfur is in group 6, so it's going to be a 2 minus. Okay, then I can crisscross them, and I can see how they would combine. Now a lot of you will be able to do this in your head, and that's fine. Okay, B, calcium hydrogen carbonate. Alright, so this is hydrogen carbonate is an example of a polyatomic ion that they might expect you to have memorized. Okay, not too hard. Calcium's a 2 plus because it's in group 2. Hydrogen carbonate. Now carbonate, you might remember, is CO3 2 minus. If you put a hydrogen in front of it, then it's HCO3 1 minus. Okay? And that's how that works. That hydrogen is a 1 plus, so it cancels out one of the minuses on the CO3, and so you end up with HCO3 1 minus. Okay? When you crisscross these, you end up with Ca HCO3 2. Okay? And then nickel 2 perchlorate. Okay, so we got to think about a couple of things here. Nickel, the nice thing about going this way is it's very easy to figure out the charge on the transition metals because they tell you in the Roman numeral. Nickel is going to be a 2 plus. Now we got to remember what perchlorate is, okay? So it ends in 8. That means there's going to be a lot of oxygens. So if we remember that chlorate is ClO3 1 minus, then perchlorate is one more than that, ClO4 minus. Okay? When we cross those, we end up with Ni ClO4 2. Okay? Alright, we'll stop there and pick it back up on the next video.